Welcome to the session of moment of inertia. So basically, before telling you much about this subject, a very important thing has to be mentioned. That is, the what does actually moment of inertia means. Actually, moment of inertia is nothing but resistance against rotation. That means this moment of inertia will give you the magnitude of resistance against rotation, and it has broad application on the on practical lives, that is on application of any design. That is, if you are designing a mechanical system, then this parameter, that is the moment of inertia, is denoted by ij, whatever may be. It is very important. Okay. Now, first of all, what we come, the first part we're gonna discuss is basically the area moment of inertia. Area moment of inertia, that is basically are of two types. One is first area moment, another is second area moment. So what do you mean by first area moment? Okay, let us start. So this is an axis system. This is x-axis. This is y-axis. Okay, and this is, suppose we are considering an arbitrary area. Okay, and here we are considering a small elemental area. That is, say, name that as dA, and this small elemental area has distance x from y-axis and distance y from x-axis. Then how will we define the first area moment? The first area moment will be defined in this way, that is q, and definitely this moment of inertia is always defined with respect to any axis, whatever maybe y-axis, maybe x-axis. Okay, so now if we want to define the first area moment with respect to y, then what will be the definition of it? That will be integration of over the area of x into dA. That is, from the name it suggests that a moment, first area moment, that is this is the area dA into x will give you the moment, the first area moment. Okay, so that means if you integrate, then definitely we'll have the magnitude of the first area moment. Okay, same for that if you go for q x, that is the first area moment with respect to x-axis, then it will be a y dA. Okay, y dA. Y is the distance of that area from the x-axis. Okay, and dA is obviously the area. If you integrate over the whole area, then definitely we'll have the magnitude of the first area moment with respect to x-axis. Okay, so this, what we are having is basically we have to construct a function. Okay, and that function what we have to construct, then we will have the integration process. Okay, another very important thing rather than that is that the second area moment. The second area moment is basically is also known as the moment of the first area moment. That is, basically, if you have it like this I, if you denote the second area moment as I, and if you write it as dt, di, an integral form, di will be equal to what? X dA is basically the first area moment. Okay, moment of first area moment, that means this x dA into the dx distance, that is the x distance we are considered here is x, then it will be x. Okay, so if you integrate this one, that is what, over the area, then you will have the second area moment, and this is obviously about y-axis. Okay, and it is denoted by yy, because basically this is the y-axis, and if you plot it up to extend this line, it will be y-axis only. So about this axis, if you define the moment of inertia, and that will provide the resistance against rotation. Okay, and basically this moment of inertia denotes or signifies the resistance against rotation. Okay, so this is the area, and this is the distance from this y-axis, and area into distance square will give you the moment of inertia of that area about y-axis. Getting my point? Okay. So now this moment of first area moment is definitely will give you another quantity. What I told is moment of inertia. Okay, same thing can be done for Ixx. That will be over the area, integration over the area, full area, that will be y square dA. Okay, that will be y square dA. From the previous one, what I told is basically inertia. Inertia is basically depend on mass. Okay, and with respect to any axis, if we want to define moment of inertia, and that will denote the resistance of that entity. Here we are dealing with the area, so definitely the resistance to for the rotation of any area will be denoted by the parameter, that is moment of inertia. Okay, or second area moment. Okay, and now these are the two terms what we derived. That is, the moment of inertia with respect to y-axis will be x squared dA. The moment of inertia with respect to x-axis will be y squared dA. Now, what we want to define is that another quantity that is basically, this is axis, that is x-axis, and this is y-axis. Suppose there is an ellipse. One is like this, another ellipse is like this. Okay, so if I am considering this locus, this ellipse as locus 1, I am considering this locus as locus 2. These are two ellipses. One is oriented in this manner, one is oriented in this manner. Okay, this is an ellipse or any figure like that, identical figure. Okay, now what I want to say is that for locus 1, we will have moment of inertia about x-axis and about y-axis. Okay, but when we are having about Iyy1 is basically the moment of inertia of locus 1 with respect to y-axis, and this is the moment of inertia of locus 1 with respect to x-axis. Can you tell me which one will be more or which one will be less? Yeah, definitely what we concluded is that more the distribution of area in space, that will denote the more moment of inertia. That means if you are considering that for this body, the moment of inertia about y-axis, the distribution is less. Okay, you're getting my point. The distribution is less. Okay, and but about x-axis, this distribution is more. This locus 1. So definitely the moment of inertia about x-axis will be more. You're getting my point. Another thing, what we can say, for same thing for this locus, locus 2, this I 2, I x 2. Which one will have more moment of inertia? That means the more the distribution of the area over the axis, far more area is there away from this axis. So basically the moment of inertia for this body will be more. That means for locus 2, the moment of inertia about y-axis will be more than the moment of inertia about x-axis, because the distribution about y-axis is more. More the area is distributed away from the axis. You're getting my point? Okay. So another important thing what I want to say is that these two are clear. The more the distribution of area away from the axis, more will be the moment of inertia. And the moment of inertia of the locus 1 about y-axis will be equal to the moment of inertia about x-axis. Okay? You're getting my point? For the locus 2, obviously, this is for the locus 2. This is for the locus 1 and this is for the locus 2. The moment of inertia will be same. Okay? Another thing what we want to define, a very important parameter, that is called polar moment of inertia. A polar moment of inertia. So before going into much detail what is the polar moment of inertia, I have to draw again the axis system like this. This is y-axis, this is x-axis, and you are considering any area like this, an arbitrary area, okay, that has particular distance, a small elemental part you are considering dA, x from the y-axis and y from the x-axis. Okay. Now, for the polar moment of inertia, you have to convert this Cartesian form into polar form. That is r and theta, and that can be, this r can be expressed with respect to any datum. If you draw a line with respect to any datum, and the datum is basically this, if you consider, and that is r. Okay, and that r can be expressed in with respect to x and y. It can be expressed with respect to the function of x and y. That is r square will be what? X square plus y square. Okay, what we are getting? So from the previous equation it is clear that this x is equal to x square dA over the area. Iy is basically integration of y square dA. Getting my point? This polar moment of inertia will be defined by a quantity which is called J. Okay, and that will be equal to integration over the area, the distance with respect to datum. Okay, the distance with respect to datum. In the previous cases, what we consider the distance with respect to any axis, and here we are respecting the distance with respect to any datum axis, and datum axis is basically perpendicular to both y and both x. Okay, suppose it is into this page. Okay, into this page, and that is mutually perpendicular to both x and y axis. Okay, and r square dA will give you the polar moment of inertia. What is the polar moment of inertia? You're getting my point? Okay, and that can be expressed in the form that this r can be expressed x square plus y square dA, and if you break this one, it will be x square dA plus y square dA, which can be eventually written as I y plus I x. Here what I wrote is basically it's little bit wrong. That ix will be, it will be Iyy and it will be Ixx, because moment of inertia of y will be x square into that area, and moment of inertia of x will be y square into dA. So this can be written as Iyy plus Ixx. Okay. So this is the form what we get is basically J equal to I xx plus I y y. Okay, getting my point? Okay. If the body is symmetrical, if the body, or here we are considering the area, if the area is symmetric, about any axis, suppose the body is a circle. Okay, the body is a circle. The area we are considering will be a circle in this case. If the area is symmetry about any axis. Okay, so what we have, this is x-axis, this is y-axis. So what we will have, the moment of inertia about x-axis will be identical for the moment of inertia about y-axis. So from this what we can conclude, because the area which is basically distributed or which will tend to rotate will be same. So this Ixx will be equal to Iyy. Another relation that can be established with respect to the symmetry. For a symmetric figure, this Ixx will be Iyy. Okay. Another very important thing that is very important for the engineers is the radius of gyration. Okay, radius of gyration. Now, if you are considering different types of beams, beam is basically a component which is basically subjected to transverse loading. Its objective to resist the transverse loading. Okay, and in this beam, if you consider the lateral section, lateral means that is there are three dimensions. We're considering the lateral one that have the area, certain area, and it may be a T section, it may be a I section. Okay, it may be a T section, it may be an I section, and the moment of inertia of different sections will be different. But the actual thing of this radius of gyration is that irrespective of the area, what we do, we basically extract that area. We extract that area into a infinitely long strip having very small width, and the distance from the axis, if you define, that will be the radius of gyration. You are not getting my point. So I am explaining it again. So basically, if this is an area, suppose you are considering a figure like this. Okay, you are considering a figure like this, and it is slightly oriented like this. A slight orientation is there. Second one. Okay. So as the orientation is very small, you cannot determine very difficult to determine the moment of inertia of two locuses. This is locus 1 and this is locus 2, which is slightly oriented. Okay. Now, in this case, what we will do, the concept of radius of gyration comes like this, because you can find the moment of inertia of individual one, okay, over any axis, suppose Iyy if you are considering, and that will be equal to ky square into a. What is the k? If you considering the locus 1, and locus 1 definitely is an two-dimensional figure which has certain area. If you extract this area into a strip, that means a strip having very small thickness, and if you have the distance k from the y-axis, then you can define this radius of gyration as this ky will be Iyy by a root. Okay, that is basically any area you are considering that can be extracted into a very infinitely long strip having very small width, that is t. Okay, and the distance of that strip from the axis y-axis suppose here, that will be the radius of gyration. And Iyy can be easily found out by the previous expressions, and the area of the strip is known because it's a rectangular strip we are considering it. So basically what we are considering is basically the dimension will be of length, because moment of inertia is basically what? Area into distance square. Area will be what? Distance square. So if you root of that will be basically a dimension of meter or dimension of length. So basically this radius of gyration is the length of that infinitely long strip from the y, because we are extracting the area in the form of a long strip, and that is very important in this moment of inertia chapter. Okay, so another very important thing what we covered is basically the radius of gyration, and that denotes the slight orientation of the areas, and basically with the help of this we can able to distinguish two figures very easily. Okay, it is very difficult on the other hand to define this radius of gyration, but the importance is very much, because if you do the analysis of, you can do that, you can severally relate measures of the size of the object, a surface, or maybe assembles a point. Okay, but this basically the application is basically for the structural engineers who basically use this radius of gyration to describe the cross-sectional area in a column around its centroidal axis. That is centroid, we all know that the geometric center of the body, irrespective of its homogeneity. So this definitely is important for the structural engineers for design. Obviously for design it is very important. And another very important thing of this part is this radius of gyration. Same thing can be written for kx also, and that will be Ixx by a. It is nothing but we are extracting the area into a strip, and the distance of that strip from the axis will be the radius of gyration. Okay. Another very important thing what we found out is basically the considering of strips, elemental strips. There are many ways by which we can consider the strips. The two basic are fundamental. One is basically the rectangular strip. Another is basically the triangular strip, what we consider. Okay. So for considering any function, for constructing any function, this elemental strip concept has to be cleared. Okay. So if you are considering for a polar moment of inertia, then definitely the strip what you have to consider is very important. Okay. Now we are coming on to another very important concept, that is basically the concept of the strip is basically you can consider two type of strips. Suppose this is a figure like this. Okay. This is a figure like this. It is a part of centroid. I'm just discussing it just to make it clear, because in the later part when I will prove the moment of inertia formulas, then it will be effective. Suppose you are considering a function y equal to k x to the power n. Okay, and this is y-axis and this is x-axis. Okay, now the definition of a centroid, irrespective of the homogeneity and the field, gravity field, was x dA by dA. Okay, and for y it will be y dA by dA. It's a single integration what we are doing. It is an area, so we can also double integrate. Okay, so as double integration is beyond the scope of this part, so I'm not discussing with it, but later I will do it in the advanced course of it. Okay, so basically this x dA, if you want to, you can consider the strip in two ways. Okay, here we will consider a rectangular strip. Two type of strip what we can consider. One is rectangular one, another is basically triangular one. So here we will consider a rectangular strip. We are considering this strip and we have to consider a function of it. So we are considering the distance of the strip as x from this datum and the width of this strip as dx. Okay, so what we conclude is that first of all we have to find the centroid of this elemental strip, and the centroid of this elemental strip is denoted by x dash, and that will be what? X, this distance with respect to datum, plus dx by 2. Dx is basically the width of this strip, and the half of this will give you the centroid. Okay, so for this strip, for the elemental strip, the centroid will be x plus dx by 2. Same thing for y dash will be what? We are considering it very small. So this f function of fx and fx plus dx will be almost same. So what we can say is basically the centroid will be fx by 2. Okay, here. So now this is nothing but x dash. Okay, basically what we proved for an centroid is basically all the elemental parts with respect to any datum, the moment, summation of all the moments will be equal to the resultant of all the area with respect to the centroid. Okay, so that was proved in the center of mass and center of gravity and centroid section. Okay, now another very important thing is that you have to construct the function. Okay, and then if you want to find out the centroid with respect to x direction, okay, then what will be the dA? dA is nothing but the area of this curve, area under the curve, and that will be a function of that will be y dx. Basic concept of integration, y dx, this is y and this dx. This will give you the area of this rectangular strip. If you gradually integrate, or the total will be what? Summation of y into x. Okay, gradual step, if you integrate or summation of all these coordinates will definitely give you the whole area. Or if you integrate this y dx, then you will definitely get the whole area. So basically this, so y dA is basically y dx. We are getting the, if you integrate, then you will get the whole area under the curve. Okay. Now this xc can be written as x dash is basically, if you approximate into x, dx by 2 is very small, and neglecting is by x y dx y dx. Okay, y is basically the function of this curve is basically k x to the power n x dx. Integrating from what? From 0. If this coordinate is basically b and this coordinate is a, that is basically a and b. So integrating from 0 to a. Y dx, you are integrating from 0 to a. And this y is basically this k x to the power n. Okay. Now, from this, you have to find out the value of k. How will you find out the value of k? We have to satisfy any point within the locus, and you are getting this point as where you are getting this point which has a and b both coordinate. Okay. So if you satisfy this equation y equal to k x to the power n, then you can able to find out the value of k. Y is basically here b, a is basically a to the power n. So the value of k is, you can easily find out. You can easily find out. Okay, by putting the value of a and b in this equation. Okay.